And thanks more generally to the Theory Fest Organizing Committee for the invitation to come speak. I've been going to STOC Foxes for a long time. I think my first one was Fox 98, which was back in Palo Alto. I've been to tons of them since. This is definitely the community that I sort of came up with as a graduate student, and it's still one that I'm, as you'll see, sort of deeply loyal to. So really an honor to be here and speak to all of you. A couple things first. So as Anupam mentioned, I am these days an additional dean at Columbia, head of research at Andreessen Horowitz, which is a venture capital firm. Rest assured I'm here in my purely academic capacity, and God forbid nothing I say should be construed as financial advice. I also want to acknowledge the very untimely passing of Luca Trevisan, who was taken from us far, far too early last week. So I recruited Luca to the Stanford CS faculty back in 2010. So as a result, I had the privilege of being his colleague and right down the hall for 4 years. Those of you that know his work know that we lost a spectacular intellect. Those of you that knew him personally know that we lost a kind, funny, and generous soul. So I want to talk today about sort of a computing functionality, technology that I think would be really cool to have, and a couple of the many scientific and engineering challenges that come up when you try to actually realize that technology. For an analogy, you could imagine 60 years ago having a vision of a technology that enabled any two people on the globe to communicate with each other near instantaneously. And you could view today's internet as some kind of approximate realization of that goal. And if we view the internet as a sort of kind of neutral global infrastructure for communication, hereby neutral meaning there's no one person or nation state that owns or operates it, really what I'm after is the analog for computation. Okay, so global neutral infrastructure for general purpose computation. So fundamentally, the functionality I want is just that of a general purpose computer, a computer that in effect has its own operating system, its own processor, its own memory, its own state. Different computer than the ones we're used to. Unlike a typical computer where somebody owns it, like an individual or a corporation, someone has root access. I want a computer that has none of those properties. Right? Basically, there's no owner, no operator. In some sense, this computer is just running in the sky for all of us to watch, kind of running as a public good doing computations. I want it to be sort of impossible almost to shut down this computer, as hard as it would be to shut down the internet. So we should have full confidence that this computer will carry out its computations correctly for a very long time. And I want it to be open access. Anyone should be able to use it. Okay, and here by use, I mean you should be able to install your own computer programs which run in this computer's operating system or interact with other programs that have been installed on there before. So a little more concretely, where is this computer exactly? Right? Is it like a supercomputer buried underneath the ocean floor? No. It's not a physical computer at all. Okay? It's going to be a virtual machine. There are physical computers involved, ideally hundreds of them or thousands of them scattered across the globe, communicating with each other over the internet, right, each with its own hardware, operating system, etc. But they're all going to be running software, common software, a blockchain protocol, via which they will coordinate on a simulation of a virtual machine. Okay? That really is fundamentally the point of a blockchain protocol, to enable a number of physical machines to carry out a coordinated simulation of a virtual machine. Okay? So why would you ever want to do this? Right? I should say. So you can sort of think of this as a protocol in the spirit of the protocols for communication that we know and love, SMTP, HTTP, etc. Notice that because this is a protocol for computation and not communication, it is going to be a stateful protocol. It needs to have memory to remember the state of this virtual machine. Okay? So why would you bother to do this? Why would you start with hundreds or thousands of computers and just get one at the end? Well, this virtual machine on the right has some pretty different properties than the physical machines on the left. Again, we talked about turning a computer off. That's sort of trivial for the physical machines on the left. You just flip the power switch, which the owner of that computer is perfectly positioned to do. Okay? But this computer on the right, this virtual machine, if you have a well-designed consensus protocol, turning this machine off is potentially as hard as shutting off the internet. Okay? Much more robust. Okay? All right, so that's what I mean by this computer in the sky, right? So why would you want one, right? There's a lot of answers to that. Honestly, if we really did have sort of powerful, robust, global shared computing infrastructure, I think there's a lot of things we could think about doing with it. Let me just give you a sort of narrower answer, but still illustrates the point which, again, if you remember nothing else, remember this, that blockchain protocols, Web3, whatever you want to call it, it's really not fundamentally about cryptocurrencies, it's not about prices, it's not about finance. It's really about a much more profound technological advance that in particular gives us ownership over things that we buy or create in the digital realm in a way that's stronger than what we've ever had before. Okay? So let me elaborate. Let me add to the picture public key cryptography, specifically secure digital signature schemes. Because let me think about sort of a signature scheme as allowing an end user to own, in a meaningful sense, a bit string, okay, like 512 bits representing a public key. And here by own, I mean someone who knows the corresponding private key. Because I claim there's at least loose analogy between the cryptographic guarantees offered by a signature scheme and the kinds of property rights that we're accustomed to in the physical world. Like, think about real estate. Like, imagine you go and buy a house, right? So that affords you various property rights, right? Like, one is called the right to use. You want to live in your house? No one can stop you. A little bit like how if you own a public key and you know the corresponding private key, you can produce valid signatures. No one can stop you. Right? Another property right for your house would be the right to exclude. No one else can live in that house without your permission. A little bit like how with the secure digital signature scheme, no one other than the owner is capable of producing valid signatures. So this computer in the sky, remember its general purpose, certainly capable of sort of verifying digital signatures. So let's couple these two ideas in a kind of trivial way and allow users to own not just 512 bit strings, not just public keys, but arbitrary digital data that lives on this computer in the sky. Okay? And conceptually, trivial. A program, maybe it's the computer's operating system, maybe it's a sort of user-installed program, it can just create pairs, okay? Corresponding of a public key, PK, and arbitrary digital data, X. We have a notion of ownership for public keys, knowledge of the corresponding private key, and so now we get ownership notion for arbitrary data just through inheritance. Okay, so you were the owner of X if you own PK, meaning you're capable of producing a signature that checks out with respect to PK. Okay? So at this point, maybe you're saying like, all right, I get it. So I guess there's a sense in which you can sort of own digital stuff like on this kind of global computer. But like, why is that interesting, right? And there's a bunch of answers I could give here, but just sort of high level, a lot of the answers kind of have the form. Owning data on this computer in the sky, it's certainly going to be interesting if it lets you do things you could not otherwise do. Maybe it lets you do things on the computer in the sky you could not otherwise do, like interact with programs there in ways you couldn't otherwise, but for owning this data X. Maybe you can exchange data X that you own for data Y that someone else owns that you would rather have. Or maybe it allows you to do things you couldn't otherwise do in the real world. It could be something as trivial as like a representation of a membership card that gets you into cool parties, a ticket, into a concert, a pass to get into a gated Discord channel to interact with your favorite musician, or it can be some sort of representation of like reputation, right? That because the computer in the sky attests to your ownership of something, maybe others know to take, for example, content you create, treat it as more trustworthy than content created by someone who does not have that analogous ownership. In any case, the high-level point here is just that once you have the right mental model for this technology, it starts becoming very easy to think of things you might do with it. There's been nice applications coming out over the last few years, and I fully expect many more over the next 5, 10 years or so. But again, what I really want to focus on is the scientific and engineering challenges that come up when you try to build the computer in the sky. And I've done interdisciplinary work most of my career, specifically between computer science and economics, but I've never seen the synthesis of disciplines required to make this technology work to its full potential. The different parts of computer science it draws on have historically had nothing to do with each other. It draws on different parts of economics that have had nothing to do with each other historically, different disciplines entirely. It's really, I gotta say, scientifically super, super fascinating, trying to figure out how to build this thing. I have limited time. I can't tell you about much of this. I'll focus on two things. First, I'll talk about some of my work on the mechanism design side. And then in the back half of the talk, I'll talk about some work being done by my research group at A16Z Crypto, bringing proof systems to practice. Okay? Before I jump into the mechanism design part, I'm just a quick comment. Your first thought might be, look, what are we? We're basically like adding extra functionality to the internet and the web, right? We're adding sort of, if nothing else, this kind of notion of stronger ownership. Like, there's already, even without blockchain protocols, there's already a ton of interesting mechanism and market design applications, stuff for us to do, right? So of course there's going to be anyways, right? I don't know, there's like, what auctions should Google and Facebook use to sell online advertising? How should Uber and Lyft do their congestion pricing, right, et cetera, et cetera. We're used to that. But let me point out, all those examples are at the application layer of the internet. Okay, stuff that operates on top, taking the functionality of the internet for granted, right? If you're talking about the internet infrastructure, right, so like 1970s, the decision to use BGP routing. The 1980s, the decision to use TCP congestion control. Right, as far as I know, no one in our community had a seat at the table when those design decisions were being made. And so what I want to highlight here is, in fact, an application of mechanism design that's at the infrastructure layer of blockchain protocols in Web3. Really sort of work done by our community, which actually shapes how these protocols are going to work, okay, which is something I don't think we've historically had in the evolution of the internet. So that's, I think, very cool. Obviously, there will be many more applications for mechanism and market design at the application layer, but this infrastructure layer application, I think, is really pretty novel. All right, so we don't need to know that much about how a typical blockchain protocol works for this talk. Fundamentally, it's, again, keeping track of the sort of evolution of this virtual machine. So fundamentally, a blockchain protocol needs to keep track of a running sequence of transactions. I want you to think about a transaction as a little snippet of assembly language code that gets run in that virtual machine, okay? And kind of all that matters for us right now is that, okay, transactions are added to this running log in batches, known as blocks. And blocks can only be so big, and they're only added every so often. Okay, so I'm going to use the Ethereum blockchain protocol as a running example. It'll become obvious why as I go along. That's the second biggest blockchain protocol behind Bitcoin. And it produces a block every 12 seconds, and a typical block might have 200 transactions. So we're talking about something like 15 transactions per second getting processed in the Ethereum virtual machine. Okay. And for popular blockchain protocols, and Ethereum certainly qualifies, the demand for processing in that virtual machine is much, much, much larger than supply. Many more than 15 transactions per second would like to have the privilege of being executed in that virtual machine. So, in this event, the blockchain protocol has no choice but to make decisions about who gets in and who gets out. And if we want to treat this sort of, as kind of neutral computing infrastructure, it makes sense to somehow include the most valuable transactions. And so that's what I want to focus on. That component of a blockchain protocol is something known as a transaction fee mechanism. And that's what we're going to talk about for the next 15 minutes or so. So what might a transaction fee mechanism look like? Okay, so let me tell you about sort of a very natural first stab. This is how it's worked in Bitcoin for the entire 15 years of its existence. This is how it worked in Ethereum until a little less than 3 years ago, something called a first price auction. So you can't expect the protocol to magically know which transactions are valuable. So an obvious idea is to have users just say so, right? A user will just include a bid along with its transaction, stating how much it's willing to pay should that transaction actually be chosen for execution, okay? Who chooses transactions for executions? Well, in Bitcoin, Ethereum, and many other protocols, basically one of the nodes running the protocol is chosen at random. It's a little more complicated if you've heard of like proof of work, proof of stake, that's where this comes in. Doesn't matter for us. One of the nodes running the protocol is chosen at random, and they unilaterally get to decide which transactions go in the next block, okay, go in the next batch. And then they collect the bids for any transactions that they include. Okay. So users submit transactions with bids. Should the transaction be included, that payment is transferred to the node that chose to include that transaction rather than others. Okay. Now, if you watched even sort of one lecture on auction theory, you know that first price auctions, while natural and sort of pretty prevalent in practice, they have, for sure one big flaw, which is the cognitive burden of trying, as a user, trying to figure out how to bid is non-trivial. You should never bid your actual value. You should always shade your value. How much should you shade your value? That depends on how much competition you have. So you have to reason about who else is bidding in the auction with you and how much they value it to figure out what the optimal bid should be. And that's actually a pretty non-trivial calculation for most of us in most cases. We've known that forever, okay? And it doesn't get any easier just because we're working in a blockchain context. In fact, maybe it even gets worse, right? This is a snapshot of the most popular wallet for the Ethereum protocol. So wallet is the software which is run client side, which kind of as a user helps you sort of submit an appropriate transaction to the protocol. This is what MetaMask, this wallet, looked like in 2020. And as you can see, like they have smart people working at MetaMask. They have algorithms which are trying to figure out what would be an appropriate thing to bid in this first price auction, given what's been happening lately. And they give you some options. But again, it's hard to figure out how to bid first price auctions. Sometimes they recommend a price that's too high and you overpay. More annoyingly, sometimes they recommend a price which is too low, in which case your transaction doesn't get included at all, even though you would have been willing to pay the going price. And then what's worse, the way Ethereum sort of works, is that transaction would sometimes hang for like 30 minutes and block you from doing anything else on the blockchain protocol. So it was really kind of disastrous user experience back in 2020 with the first price auction. So, given that, the obvious question to ask is, can we have a smarter, more sophisticated, better for users transaction fee mechanism, right? Most extreme, the holy grail here would be sort of the same kind of properties we get from a second price auction or a Victory auction, which I hope most of you have seen before. That's an auction which is truthful in the sense that it's always a dominant strategy. It's always optimal for you to just figure out the maximum willingness to pay and report that to the mechanism. So one question would be, can we have a better transaction fee mechanism which is truthful in the same sense of a second price auction? Okay. So I hope this seems like a really basic question, right? So demand exceeds supply in a blockchain protocol, got to decide who gets in, who gets out, got to figure out who pays what. Okay, hopefully that seems like a very basic mechanism design problem. It turned out, at the time I did the work I'm going to describe, which was in 2020, it was also a very sort of timely and practical question. Okay? How did I know it was a timely and practical question? Well, honestly, it was like the practitioners kind of just told me so. So let me tell you a little bit about the backstory here. So I think it was around like 2017, a time at which I was super focused on my research. I was just kind of focused on writing research papers. I mean, I still am, but it was kind of even more back then. And I started getting these like phone calls I'd never really gotten before. I guess 2017 was also long enough ago that I answered my phone with positive probability, which is probably no longer true. But in any case, back then I would sometimes answer it, and it would often be some kind of young 20-something, entrepreneur with like a 4-person startup, and they would say, they'd be like, "We need exactly your skill set for our sort of new crypto project. Okay? We need a computer scientist, someone with a PhD in computer science, but who also deeply understands mechanism design." And for me at that time, this was sort of coming out of the blue, out of left field. Right? It's true, there was a lot of demand for computer scientists who know mechanism design from like big tech, like Google, Facebook, etc. But not a lot, in my experience at least, from the startup world, and like I wasn't really paying attention to the crypto world at all at that point. And honestly, like, I was pretty skeptical, right? Some kid just like calls me up, I'm like, how would you know what my skill set is, and how would you know if my skill set is like helpful for your project, basically, right? And usually, how do they even know who I am? Usually it just so happened they stumbled on my YouTube lectures for algorithmic game theory. In fact, usually the only reason they'd ever heard of the phrase mechanism design was because it's in lecture 2 of the 20 lectures in algorithmic game theory. So they would sort of call me up. And, I honestly, in 2017, I kind of ignored them all. I didn't really take it very seriously. Part I just had a lot of other stuff I was working on that was exciting. In part, I wasn't convinced the work was going to be sort of interesting or deep enough to be worth it. But it did kind of plant a seed, honestly, kind of in 2 ways. Like one is just, I don't know, when you're a theoretician, like us, like it's just not every day that there's this kind of like organic demand like for your exact skill set coming from somewhere else. And so part of me was like, well, maybe the universe is like trying to tell you something, you should try to like pay a little bit of attention. The other thing that sort of occurred to me was like, look, like, the biggest theme throughout my entire career has been this kind of focus on computer science applications that benefit from non-trivial economic or game theoretic reasoning. And one thing that's been fun about sort of having that consistent focus is this naturally led me on this journey from like application domain to application domain. Network routing and design, online advertising auctions, spectrum auctions, et cetera. And so it sort of occurred to me, it's like, maybe like blockchain protocols and their applications could be like a really interesting application domain for that exact interface, right? And I now know it definitely is. But probably the first time that occurred to me was at this time in 2017. A few of you saw that, excellent. So fast forwarding a little bit, this is now early 2020 when members of the Ethereum community reached out to me. It wasn't a phone call, it was an email, so I actually responded to it. Everything okay? Okay. So members of the Ethereum community reached out to me with exactly the problem I just mentioned. Right? So they had been running this first price auction up to that point until early 2020. And in fact, there was a really quite polarizing debate happening in the Ethereum community at that point, okay, in 2020. Because it turned out there was a new proposal for a more sophisticated transaction fee mechanism. Some people loved it, some people hated it, lots of people just didn't understand it at all. Right? And they wanted my help assessing whether or not it was a good idea to switch to this new transaction fee mechanism, okay, which I'll tell you about either on the next slide or shortly thereafter, okay? And the sort of the Ethereum community, it's sort of very much in the spirit of sort of strong open source communities. So they would really do a great job of when something is polarizing, sort of trying to come to a community consensus, right? That was part of why they sort of reached out to me. They also did this sort of survey of various stakeholders in the ecosystem. Again, this was done in 2020. Tim Biko being kind of a key member of the Ethereum community. And they said, look, EIP 1559, which is the new transaction fee mechanism they're thinking of switching to, thumbs up, thumbs down. If you don't like it, what can we do to make you more comfortable with maybe making this big switch? Okay. And the respondents said a few things, right? But the thing I want to highlight, right, is this underlined part, which is the lack of a formal specification or analysis of exactly what this mechanism has. And I want to emphasize that none of the respondents of this survey are the kind of people that write research papers. I mean, these are people that were miners. This was back in the proof of work days in Ethereum. Or they sort of ran wallet software like MetaMask that we talked about. They're all people building things in the Ethereum trenches, right? And there it is, like in writing, there was really a visceral hunger for exactly the kind of rigorous research that people in this room do. Okay? And this was definitely one of my big sort of reasons, motivations for spending a chunk of my life in 2020 working on this project. Okay? All right, so that's kind of the setup. You think about the problem, I think it's totally reasonable to kind of say, surely this is well solved. Like whatever, you have finite block space, some stuff gets in, some stuff gets out, you gotta figure out how to price people, whatever, right? Open up a textbook, copy, paste an appropriate solution. And I think that's a fine sort of initial instinct, right? But as often happens, once you sort of delve into the idiosyncrasies of the application, you realize there's other parts of the problem which you hadn't been modeling previously. So I actually wrote a blog post, 8 reasons why mechanism design for blockchains is hard, 8 things that are sort of constraints on what you do that are not there in more traditional applications of mechanism design. Transaction fee mechanism design illustrates many of these, 8, not all of them, but many of them, as we'll see. So let me spell those out on this slide. Okay? I'm going to have a list of challenges. The first challenge I've labeled challenge number 0, because there's nothing special about blockchains. It's just the problem you always have when you're designing a mechanism. Okay? When you're doing mechanism design, the problem is you don't know what people want. You don't know how much people value their transactions. You wish you knew people's preferences, because then you could try to make a decision that was good for everybody. So you try to elicit information about their preferences and then make a good decision. And what you're always worried about is that people are going to try to game your mechanism, that people might misreport what they actually want, because it's going to trick you into choosing an outcome which is actually better for them than it would have been had they just reported honestly. Okay? So that's always the challenge in mechanism design. And we have language saying mechanisms that do not have this property, that are not gameable in this way. Okay, sometimes they're called truthful mechanisms. I'll probably usually call them basic mechanisms, dominant strategy and semi-compatible. But again, that's just the same thing as a second price auction, same thing as a victory auction to the VCG mechanism. So the next couple of challenges are unusual, okay, compared to traditional mechanism design. remember at the beginning when I said, how do these things work, right? I said, how is the next block added to the running log? One node running the protocol is chosen uniformly at random, okay, and gets to have unilateral control over that block, okay? So in other words, you have no idea who it is who's actually going to be carrying out your mechanism, who's choosing who gets in and who gets out. So, as a theoretician, you can kind of sit in your armchair and like write out this description of this really cool mechanism. Oh, it'd be really cool if the nodes running the protocol sort of included these and excluded these and et cetera. But they can do whatever they want. Okay? And that's not normal compared to like a spectrum auction where the government is running some auction that was agreed upon long in advance. Okay? So when you design your mechanism, you have to take into account not just the incentives of the user, but also the party responsible for carrying out that mechanism. Okay? There's no chosen at random to decide upon the next block. So that's going to be part of this MMIC constraint, which I'll talk about. The other thing that this randomly selected node or block producer can do is it's fully capable of just, inserting its own transactions if that would, for example, increase the revenue that it makes. Okay? And just sort of looking ahead a little bit, this is exactly why second price auctions become so problematic in a blockchain context. Right? If I get a bunch of transactions with bids like, 10, 8, and 6, I can just make up a transaction with a bid of like 10 minus epsilon to make sure that I get, basically the revenue of a first price auction rather than a second price auction. So that will also be part of the second set of incentive compatibility constraints, this MMIC definition. Finally, and this is one of the sort of challenges I highlighted sort of in that blog post, was collusion is sort of much more of a concern, usually in a blockchain setting than in traditional applications of mechanism design. One reason for that is just it's easier to sort of coordinate through the smart contract functionality that blockchain protocols offer. Another reason is just that you kind of just you can't lean on the rule of law as much as you can in a traditional mechanism design setting, right? Like in a government spectrum auction, basically all the participants, you just make them sign a contract and say don't collude, and if you collude, you're going to get busted and there's going to be punishment. And there's not really sort of a great way to implement that idea in a permissionless blockchain context. So there's this much stronger incentive to try to design mechanisms which just automatically within the protocol discourage collusion. Okay? And that was a key design decision, as we'll see, behind EIP 1559. And so in my work, what I did is, so again, the DSIC constraint is old. The MMIC and OCA proof notions are new to this work, okay, necessary to capture the idiosyncrasies of the blockchain application. And then the theoretical question is, could you have a transaction fee mechanism that satisfies all three incentive compatibility guarantees simultaneously? Okay. All right, so I have a couple of slides with more details on the two new incentive compatibility notions. I'm not going to really read through these. I think both of these are kind of exactly what any of you would write down, given what I've already told you in English. So MMIC, again, that just says, you can write down instructions for what this randomly selected block producer is supposed to include or exclude, but it's going to do whatever it wants. So you better write down an allocation rule, you better write down a mechanism that's in its best interest, that's actually revenue maximizing for the block producer. Okay? Moreover, you should disincentivize the injection of any fake transactions. And as we mentioned, the whole reason you're never going to see a second price auction or a VCG mechanism in this talk is because of this. It's very easy to manipulate through these injected transactions by the block producer. The other new incentive compatibility notion is OCA proofness. This is the one about collusion. So collusion specifically between the block producer, the person selecting transactions, and the users. And so this just says there should not be an incentive to collude in that way. So the group will not be better off through colluding. And again, the main thing I want you to take away from this is I again want you to notice that there's a format that you'd be tempted to copy paste from a textbook that you can't exactly because of this constraint. And that's the idea of using a reserve price, okay, or a minimum bid. So to see the problem, imagine you tried to say, hey, let's use a mechanism where there's a reserve price of $10. Anyone who bids less than $10 is automatically ineligible. Now consider a situation, right, where you've got a whole bunch of users, all of them value their transactions at like $7, right? And then you've got this block producer responsible for choosing who gets in and who gets out. If the block producer does what they're supposed to do, they're supposed to say, sorry everybody, nobody's above the reserve price, I'm just going to publish an empty block and make no revenue. Notice everybody would be better off if instead the block producer said, hey everybody, just between you and me, make sure you bid $10 like to the blockchain protocol so that you're eligible for inclusion, and I'll refund you $250 off-chain, okay, through a side name. Okay. So using reserve prices, at least in the most naive way, you cannot do because of this collusion resilience requirement. All right, so that gives us three dimensions along which to assess a TFM DSIC, MMIC, OCA proof, the three notions of incentive compatibility. We'd like all of them. So now let's actually turn to the challenger in the Ethereum TFM battle. Right? The incumbent is that first price auction. The challenger is this newer proposal, EIP 1559. Not my proposal. It was proposed by Vitalik Buterin, who's also the lead founder of the original Ethereum protocol. I would say three big ideas here. Idea one is to actually use a reserve price. And you're like, wait a minute. I just said you couldn't do that because you'd be sort of susceptible to collusion. Okay, I said you'd be susceptible to collusion if you do the obvious thing with the revenue generated from the reserve price and you pass that on to the producer of that block. It turns out if you redirect that revenue elsewhere, and in particular what this mechanism does is just literally burns that revenue, removes those coins from circulation, then in fact, as we'll see, you can have collusion resilience. So that's idea number one. A reserve price, transactions that bid below this, or ineligible revenue generated by this reserve price, this base fee, are burned. Okay. So the next question is, where does the reserve price come from? Okay. And the idea here is pretty simple. You're going to use local search. Right? So if the reserve price currently looks too high, you're going to lower it, and vice versa. How would you know? How would you know if the current reserve price is too high or too low? Well, the second change to the Ethereum protocol was to, rather than just have a hard cap on how big a block could be of 200 transactions, you made it a soft capacity. So you said, let's have a target of 200 transactions per block, but we're willing to go up to 400 if we really need to. And so now you can use the size of previous blocks as your sort of local on-chain signal about whether to raise or lower the reserve price. If the last block was too big, 300 transactions, then you should raise it. If the last block was too small, like 100 transactions, then you should lower it. Okay, so it's just constantly doing local search every 12 seconds as these auctions keep getting run over and over again. Okay? Finally, there's kind of like an emergency backup first price auction. And so the way that's implemented is users always have to pay the base fee, the reserve price, no way getting around that. Optionally, they can pay some extra above and on top of the base fee, which then gets transferred to the block producer like bids did back in the first price auction. Okay? And so the idea here is if for some reason bidders need to compete, this bidding mechanism, this bidding is the mechanism by which they would do that. So we've got our criteria, our three notions of incentive compatibility, the one old one, the two new ones. We've got a formal description of our challenger, so now I can ask, how well does it do? Okay. Well, how well does the incumbent do, the first price auction? Okay. Definitely not truthful. Never bid your true value in a first price auction. You always want to shade your bid. Okay, so it's never truthful, never DSIC. Not hard to see it satisfies the other two properties. Part of the reason that it's done well so far. Meanwhile, you can prove that the EIP 59 mechanism, so first of all, honestly, it's just kind of a lot more satisfying because it's just really tailored to the blockchain setting. First price auctions, you could make up that mechanism for any number of applications that have nothing to do with blockchains. You would never come up with EIP 1559 unless you were thinking about blockchain protocols. Right? You're exploiting the fact that one of these is run every 12 seconds, so you're getting constant feedback about what the reserve price should be. You're also using the fact that the blockchain has a native cryptocurrency, ETH, which is what allows you to credibly burn the revenue generated by the base fee. In exchange for taking advantage of these kind of unique aspects of the blockchain setting, indeed, you get a Pareto improvement over the incumbent. Okay, so EIP 1559, it still has those same MMIC and OCA proof guarantees, but now it has DSIC almost all the time, okay, in a formal sense. So there's a particular edge case where EIP 1559 is not DSIC, an edge case where the reserve price, for whatever reason, is just way too low. Then it basically gracefully reverts back to a first price auction. But outside of that edge case, it is indeed a truthful mechanism. Compare that to the first price auction, which is literally never truthful at all. Okay? So that's a sense in which it's a strict improvement in incentive compatibility. Okay? Obviously, you'd like to get rid of that usually. It turns out it's sort of a new result, joined with Elaine Shi and Hao Chung, shows that you can't. Okay, so this will appear in EC next month. So in some sense, EIP 1559 is optimally incentive compatible. So it's a very strong sort of theoretical justification for potentially adopting that mechanism. I want to keep this talk mostly focused on the theory, but I do just want to sort of quickly say, and we'll see another example of this at the end of the talk, the pipeline from theory to practice is kind of as short as I've ever seen it in this area right now. So it's pretty wild to be working at it, actually. So EIP 1559 was indeed adopted, right? So my report came out in December 2020, and Ethereum did a sort of upgrade or hard fork in August 2021. And EIP 1559 has been happily running ever since, okay? Obviously, I don't know the counterfactual. I don't know what would have happened if I hadn't run my report, but certainly many members of the community have said that my report was important for getting support for the change kind of over the line. And certainly it was the standard reference when there was a lot of media attention coming out around the time of that switch. There's even like some cute little dashboards which are sort of tracking how much ETH has been burned over the time because of the switch to EIP 1559. People get kind of into sort of following that. So in the remainder of the talk, I want to say a little bit about a different ingredient that goes into making the computer in the sky the best version of itself. Okay, and it's something that really touches on something very core to the theoretical computer science community, namely proof systems. So I'm going to talk a little bit about that. This is not my work, this is not my expertise, but it is work that's done in the lab that I direct at A16Z Crypto. So we mentioned this in the previous part, that the computer in the sky, or at least the version put out by the Ethereum protocol, is slow, 15 transactions per second. And for this technology to really realize the full vision of what it could achieve, that number needs to get a lot bigger, right? Certainly 2 orders of magnitude for sure, ideally 3 or even more orders of magnitude bigger. That's where we need to get to. So what's the plan, okay? How are we gonna get there? How are we gonna get much more powerful computer in the sky? Well, a lot of people, a lot of smart people have been working very hard on this for several years, and there's a bunch of competing approaches, okay? So I'm now gonna sort of walk you through kind of a decision tree, okay, of different approaches to how you would scale up this computer in the sky. We'll eventually end up at a leaf of the decision tree where proof systems are kind of both necessary and sufficient for it to actually be a viable scaling strategy. But I do want you to know as we walk through this decision tree, this journey is actually going to give you a pretty accurate map of exactly where the blockchain infrastructure industry is right now. Like every branch of this tree, there are like multiple projects with dozens or hundreds of really smart people trying to get it to work and tens or hundreds of millions of dollars of funding to help them do it. Okay, so there's really kind of just a big competition about all of these different ways. I have no idea which way is going to win. Honestly, at this point, it just feels like I have a front row seat of this very evenly matched kind of sporting event, and it's actually extremely sort of entertaining, to be honest. It's very, very fun. So top node of the decision tree. How are we going to make this computer in the sky faster? Okay? In some sense, like the most direct way of doing it is like, well, let's just kind of improve its hardware and its software, in effect. Remember, I showed you that sort of 5x5 grid of the physical machines, sort of running this blockchain protocol. You can say, well, first of all, make sure those physical machines are really, really powerful, like big, beefy servers with really, really good internet connections. And secondly, do some really, really cool cutting-edge computer science to make the consensus protocols as powerful as possible. So that's approach number one. And actually, many of the more recent generations of blockchain protocols from the last, say, 3 or so years are taking this approach. Solana is probably the best known one, but there's also some other very promising ones. Okay. So that's one idea. The other branch of this decision tree is like, no, and this is the route Ethereum has taken. Let's go ahead and embrace the idea that we have this very slow computer in the sky, and let's scale it up through a hierarchy. So let's add layers. Let's supplement the slow computer in the sky with fast computers that are sort of on the periphery. So that's what I'm showing you here with these spokes around the sort of basic Ethereum computer in the sky. So in this context, these spokes, these are sometimes called layer 2s, and then the original Ethereum protocol, the slow one, is called the layer 1, or sometimes these are called roll-ups, because basically you're sort of rolling up a whole bunch of computation you would like to do on this computer, and doing them, shipping them off and doing them instead over here. Okay? So rather than, the sort of general model here would be that users would not interact directly with the layer 1, like with the Ethereum protocol. They would interact with one of these layer 2s, and it's only the layer 2s that would interact with the layer 1s. Okay? So this is the branch of the decision tree we're going to go down next. So I want to talk about different ways you can try to do this scaling through the addition of sort of supplemental off-chain computation. Okay? So notice these spokes, I've drawn these as laptops without a cloud. So these may or may not be blockchain protocols in their own right. For simplicity, think of this as actually just being like a big, beefy server owned by a single company. Okay? At which point, and that's where users by default are submitting transactions, right? And at that point, you're kind of saying like, well, what was the point of this whole endeavor anyways? Like, I thought the whole reason we built this is so that like no one could turn it off, and it was like very reliable, and it had no owner. Now you're telling me users are just going to interact with these sort of corporate-owned single machines anyway. It's like, why are we doing this? And the vision is to try to get the best of both worlds, right? That 99% of the time, or 99.9% of the time, right, a user is just happily interacting with sort of a big beefy server that's doing everything it's supposed to be doing. So it's the exact same user experience you'd have today with any sort of typical sort of web application. On the other hand, the layer 1 will serve as a safety net, okay? As a sort of fallback mechanism should anything go wrong with this layer 2 machine, which again is just a single machine, right? So this company could go out of business, it could just sort of crash and go offline, who knows, okay? So the idea is the layer 1 will serve as sort of the safety net for the kind of safe operation of all these spokes at the edges, okay? Now, so what's the interaction look like between the layer 2 and the layer 1? So the first idea is just the layer 2s are going to just periodically notify the layer 1 about their state. Okay? So just to be clear, right, this is the same computer this guy had before, has its own operating system, its own processor, its own memory address space. Same thing for all of these. All of these also have their own state, their own memory space. Okay? So each of them will periodically just notify the layer 1 and say, hey, here's the current state of this machine. All right, it's not going to actually send that, right? That would be too big. It'll send a cryptographic commitment to its current state. Okay, so something like the root of a Merkle tree. Okay? So all of these layer 2s will be periodically submitting cryptographic commitments to their current state to the layer 1. And that already gives you some non-trivial functionality, right? So that allows you to be robust to crash faults, okay, to these layer 2s kind of just going offline, like the company going out of business. Okay? Why? Well, a commitment to the last state of the layer 2 is sort of living here, ideally forever, on the layer 1. And so what that means is that if there's anybody that knows the history of transaction processing on this layer 2 that went down, they're in a position to reconstruct the last state of that layer 2, from which you can fire up some other beefy server to resume operations where you left off. So because you have a commitment enshrined on the layer 1, there's no way to fabricate a bogus state of that layer 2. Right? The only one you could possibly come up with would be the correct one, the one that's consistent with the commitment. You might ask, who's going to know the transaction history of the layer 2? Actually, today, there's sort of an extreme solution, which is the most sort of popular roll-ups, literally just post the description of the transactions they process to the layer 1. So they survive on the computer in the sky for everybody to see. So literally anybody can reconstruct the layer 2 state just from what everybody knows from the computer in the sky. In the future, you can imagine third parties providing the service instead. Okay? All right. So that's just to tolerate liveness failures. If the layer 2 goes away, as long as someone knows the history of its processing, you can resume where it started. Okay, so that's, again, using the layer 1 as a safety net. But what about sort of safety failures? What if you actually have a malicious layer 2 node that's online but posts a commitment to a state which is not the actual state of that layer 2? And this is not hypothetical, right? I mean, these layer 2s in general are going to be hosting digital assets which are potentially very valuable. So there's actually a very strong incentive for one of these layer 2s potentially to post a commitment to a memory, to a state in which the operator of that layer 2 just so happened to wind up with all the assets of all of the users of that layer 2. Okay? So what's really important, okay, is that you can actually deal with safety failures. That if one of these layer 2s posts an incorrect commitment, then in fact you should be able to detect it, correct it, etc. Okay? So we have another branch here of the decision tree, different ways to sort of deal with these safety violations. The one which is more common right now, if you've ever heard about optimistic roll-ups, this would be that category. The one which is more common now is sort of a very quick and dirty approach, which is just kind of like a detect and then fix it after the fact. Because notice that, again, under these sort of same assumptions, as long as someone's aware of the transactions that have been processed, anyone can catch this malicious layer 2 when they post sort of an incorrect commitment. Right? If someone else also knows the state of that L2, they can notice that the commitment is not the correct one. And then you somehow take pains to sort of fix things after the fact. And I don't want to get into the details of how that's done. Pretty much everybody agrees that if you put performance considerations aside, what would be much, much, much better would be to instead deal with this proactively. Rather than allow safety violations, so bogus commitments, and then fix it after the fact, why not just cryptographically prevent them from ever being posted in the first place? Okay? So ideally, now, each of these layer 2s would post, along with its commitment to its current state, along with that, a proof that that commitment was computed correctly. Okay, that really it does represent the actual current state of the layer 2 as opposed to some fabricated one. Okay? The idea is that then this proof posted by the layer 2 to the layer 1, that would then be verified by the computer in the sky. That would be verified by the layer 1. Okay? The layer 1 could then just ignore anything posted to it that's not accompanied by a correct proof. Now, for this to make any sense at all, remember, this layer 1, this is supposed to be a really slow computer. These are supposed to be fast computers. Not only that, there might be hundreds of these fast computers all periodically posting commitments to the layer 1. Right? Think of each of these as every minute or every hour sending something to this computer in the sky. So verifying better be very lightweight for the layer 1. Okay, that better be much, much, much faster than it would have been to actually do that computation originally. Right? Otherwise, this makes no sense. We're trying to offload computation from the layer 1 to the layer 2. Verification better be way, way, way cheaper than actually doing the execution. And now at this point of the talk, I hope you can start to see why this is in the wheelhouse of proof systems, and actually very specifically in the wheelhouse of SNARKs. Right, so the S in SNARK stands for succinct. That is exactly this property, that verification of the proof should be much, much, much faster than redoing the computation from scratch. The N in SNARK stands for non-interactive, right? And that is what we have here. Really, we want the layer 2 to just post once and for all a proof to the layer 1. The layer 1 checks it, and you're one and done, and you proceed. Okay. So just to be super concrete, this is so for this vision to work, this is the computation that we need a SNARK for. Okay? So to describe this, right, I need to tell you sort of what's the witness, and I need to tell you the computation that gets done by the prover given the witness. Okay? So again, just to remind you here, the verifier in this context is the layer 1, which is slow. The prover in this context is the layer 2, which is fast. Okay? It has more knowledge. So specifically, the witness here is supposed to be what the layer 2 knows. It knows the last memory state to which it committed. It knows the transactions that it processed. The computation is just to process those transactions and compute the new commitment. Okay? So the corresponding Merkle root given the new state after the processing of all of these transactions. Okay? So this is the computation we need to SNARK for. And let me point out, you should think of this as really general purpose computation. Right? Like if all of the transactions were just like payments from some Alice to some Bob, you could maybe talk about sort of specialized SNARKs. But for a Turing-complete blockchain protocol like Ethereum, right, the fact that there are sort of arbitrary transactions in here being executed, this is really arbitrary code. So you really need a SNARK, specifically a practical SNARK for general purpose computation. Okay? And it's really not an exaggeration to say that this approach to blockchain scaling Ethereum, is viable if and only if sufficiently practical SNARKs for this computation exist. A lot of people right now really, really, really care about scaling Ethereum, so a lot of people really, really care about whether sufficiently practical SNARKs for this computation exist. What does sufficiently practical mean? Different things you might care about. You care about sort of the work of the verifier, or the L1. You care about the work of the prover, or the L2. Because remember, this is not a metaphor. This is not a Merlin. This is not a wizard. This L2, it's a faster machine than the computer in the sky, but it's a physical machine. Okay? There's only so much work we can ask it to do. Okay? So for 30 years, we've known that SNARKs for general computations exist in principle. And this, again, honestly, this is a statement that if you weren't trained in theoretical computer science, I think this would seem like totally nuts. This would seem like impossible, right? It's one that if it's something like specific computation, right? It's like long division, you know, like maybe there's some way to have a proof which is much quicker to verify than kind of doing it from scratch. But like, this is arbitrary computation. I tell you nothing about it other than it's represented with a circuit of a given size. Can you really compress anything? Yes, you really can compress anything. So Killian and Macaulay showed how to do that in principle. So the highlight basically is almost kind of follows black box from the PCP theorem. So the idea of what the proof looks like, so the prover sends a cryptographic commitment to a probabilistically checkable proof of the computation that it's supposed to do. Now, normally to check a PCP, right, you ask a sequence of queries. Here we want something non-interactive. So at the end, you do something known as the Fiat-Shamir heuristic, which takes a public coin interactive protocol and turns it into a non-interactive protocol. Basically, rather than relying on a verifier to supply random challenges, you just rely on a cryptographic hash function to supply those challenges as a function of the previous messages of the prover. That is weird. J. Okay. Okay. So that's the idea of Killian and Macaulay, right? And so for 30 years, the question has been, can you make this practical? There's been a tremendous amount of work. Probably 20% of the people in this room have done work that have contributed to this 30-year long line. And really just circa kind of now, the answer is starting to be yes, literally, circa kind of now. Actually, I was on a call with Noam Nissan earlier this morning, and he literally said, if SNARKs can be made practical, anything can be made practical. Right? And that's sort of exactly what it is. Good. So really what you need, so lately the bottleneck has really been prover time. Okay, so you need a prover time that is not just polynomial time, but really linear time, and you really care about the constants. To give you a sense, if you had like a constant overhead of 1,000, so if doing a computation plus proving it correct was 1,000 times slower than doing the actual computation, that would be really good, actually, if you had an overhead of 1,000. Overhead of 1,000,000, not useless, but not that good. Overhead of 1,000,000,000, basically useless. Okay? And that's the constant in front of the linear time of the proof time. Okay? So there's been a bunch of breakthroughs by many different groups over the last couple of years that have been making great progress. I'm going to just focus on one of them. Okay, it's the one that, full disclosure, it's the one that came out of my research team. But it's also, I think, one of the ones with the most momentum, one of the most promising approaches. Okay? And obviously, I have to just do this very quickly, but one insight is that a lot of the concrete inefficiency of the Macaulay, this is reflecting my approximation algorithms background. So, Killian-Macaulay approach is that in some sense you redundantly remove interaction. Okay, at the end of the day, you need a non-interactive proof. And that's why at the end of the day, they use the few-Chimere heuristic to not do the sequence of queries to the PCP. But if you remember the origins of PCPs themselves, they in some sense are also meant to be removing interaction with some like prover which you've then since gotten rid of. Right? A PCP is almost kind of just enumerating what a prover would have answered to for every possible challenge a verifier might have asked it. So that can also be thought of as an interaction removal step. And also they're kind of like different in character, right? Because like that PCP removal of interaction, there it's this enumerative character. Like you're thinking about like everything you might have asked and answering them all. Whereas feat-Chimere, it's not like that, right? It's literally you only bother to answer the challenges you have to, given the output of the cryptographic hash function on the various sets of prover messages. So the idea then is, given that we're going to use feat-Chimere at the end anyways, why not just really lean into interaction and sort of just maximize the power of interaction until the very end, until the final feat-Chimere step. So we want to ask ourselves, what would be a tool that sort of really showcases the power of interaction? Okay. So I think I have time for a little digression. So I've been around a while, not as long as some of the people in the room, granted, but for sort of like 25 plus years. And so I've seen a lot of different scientific communities, both in computer science and outside, kind of evolve in parallel over that time. And honestly, some have done much better than others. Okay? And it's interesting to think about the reasons why. Right? One is obviously just the quality of the work. And obviously the stock box community scores as high as you can score on that metric. But other things matter too. Another thing I think this community is really good at is sort of celebrating the past. Okay? Recognizing that the great work that we're doing right now stands on the shoulders of several generations of brilliant theoretical computer scientists that came before us. And so I think generally we do a good job of telling the stories, encouraging our students to go back to the original sources, learn the motivations for all of the definitions that we now know and love, understand how we got from there to here. And because of that, I'm sort of counting on this fact that I think we're very strong in the lower category, theoretical computer science, that when I say what would be a tool that showcases the power of interaction, actually a lot of you will think about the same thing that I'm thinking about, right? Which is the sequence of ideas in sort of 1989 and 1990 that led to a bunch of huge complexity theory breakthroughs culminating in IP equals P space. And in particular, I want to highlight a key technical tool in this whole line of argument, which is the sum check protocol. Okay? So the sum check protocol, for those of you that remember it, so that's basically a way to do discrete integration of a multivariate polynomial. The bad news about the subject protocol is that it needs many rounds. It provably needs many rounds. One round for each variable in the multivariate polynomial. The good news is that at least if the polynomial is low in each degree, the prover does not have to send much to the verifier in each round. Okay, so it's very sort of communication efficient. So it's long, but very communication efficient in each round and overall. And so indeed, the approach towards SNARKs, which has come out of my group just very recently, this is exactly the philosophy. To lean into the sum check protocol, in some sense maximizing the power of interaction, all the way up until the final Fiat-Shamir step. In effect, given that we're sort of going to be doing sum check, they're going to be doing sum check, and then passing the Fiat-Shamir, the fact that there's so little communication from the prover to the verifier in each round of the sum check protocol winds up translating at the end of the day to a non-interactive proof where the prover does not have to cryptographically commit to very many things. As it turns out, in the modern approaches to SNARK design, a lot of the prover work actually comes from the number of cryptographic commitments that they have to make. So if you have an approach which substantially reduces the number of field elements you have to cryptographically commit to, really good chance that's going to translate into a commensurate speed up in the prover time. Okay. So that's the key idea behind this new proof system, which came out in 2 companion papers, Lasso and Schultz. These both appeared in Eurocrypt, so they just were presented literally like 2 months ago. So Justin Thaler, so he's sort of full-time on the research team at A16Z Crypto. Srinath Sethi, he's a researcher in Microsoft Research. Robbie is an assistant professor at CMU. Arzu Arun just finished his PhD at NYU and was our intern at A16Z Crypto 2 years ago, which is when a lot of these ideas sort of got finalized. Okay. So this is 112 pages of hard theory, right? The kind of hard theory that people in this room do. It's a little unusual in that it's hard theory where the exact goal is to try to say that instructions are going to do things more practical than we had before, right? And it's hard to really convincingly make that case unless you build it. Right? So someone would have to build this 112 pages of hard theory. Right? And so we actually did that. Okay? So in addition to the research team at A16Z Crypto, we have an amazing engineering team. And 2 of the engineers, right, Michael Zhu and Sam Magsdale, spent about 6 months turning these proof systems into something real, okay? Into something you can use. It's open source. This is the GitHub repo over here. It has been benchmarked and compared to other state-of-the-art, and it is at worst competitive with the other leading approaches, and at best superior. Again, I do want to say this is not the unique breakthrough that's happened recently. There's a bunch of different projects sort of leapfrogging each other, sort of basically in a very heated race. Again, it just feels like having a front row at a very fun sporting event. But this is real. Okay, so this really has been built, and it really is the original hope that really leading into interaction the entire time, maximizing that in the construction, actually really does lead to significantly faster prover times, and therefore gets us closer to that full vision of verifiable ones. Again, it's sort of surprising how much relatively mainstream media attention sort of get sort of working in this area. True to form, the media attention is often like very inaccurate. I don't know why, but when people think about SNARKs, they always want to throw in the acronym ZK, whether there's zero knowledge or not. Right? My focus here has really been on the S, the succinctness, but people just love the acronym ZK, I've got to tell you. Everyone who's StockFox trained is fighting what I fear is a losing battle, trying to get people to use these terms correctly. But we're trying. We're really out there trying. Oops, sorry. So, I'm almost done. When you look at this slide, I hope the people in this room, I really think you should feel a sense of pride, identifying as a theoretical computer scientist, as a member of the StockFox community. Like, this is very unusual, right? This split screen, where you have, on one hand, like extremely scientifically and mathematically deep theory, and almost kind of in real time, right? That's simultaneously, fundamentally shaping the trajectory of what might really be the next generation of the internet. It gives us just much stronger property rights for digital assets than we've ever had before. This is very unusual, okay? And I don't think this is an accident. Okay? I think there's sort of unique features of the StockFox community that makes this possible. One, honestly, is just intellectual horsepower. Like, I don't know of other rooms I would walk into that would have the degree of intellectual horsepower as this one. But it's more than that. Right? So I talked about lore earlier. But sort of broader than that is really, I'd say, culture. I'd say TCS, for all the amazing sort of definitions, theorems, proof techniques that have come out of this community, I think one of the reasons it has remained so healthy and vibrant for my entire career has been the culture. Right? So for example, I think on the one hand, we hold ourselves to sort of almost impossible standards of science, just extremely, extremely ambitious. While at the same time, and I say this from experience, as someone that came up in this community, very nurturing and sort of mentoring of the younger generations. Right? And I see, as I always do at this conference, a tremendous number of students in the audience, who I'm sure, as always, are being well taken care of by this community. And so speaking of TCS culture, right, so just to wrap up, like everyone in the room, right, I'm sure you were ecstatic to hear, like I was, that this year's Nobel laureate is Avi Victorson. Avi obviously, more than deserves the award purely for all of his incredible scientific contributions, no doubt about that. But in my mind, sort of almost or equally as important has been the contributions to TCS culture. I can't think of anyone that has had a more positive and lasting effect on TCS culture and the health of this community than Avi. So I just wanted to wrap up by saying, Avi, congratulations on the Turing Award lecture, very well deserved. Everybody enjoy the week. I've seen a lot of scientific communities, and none of them are quite like this one. So thanks very much.